Hi everyone, my name is Abby Leonardi, and I'm here today with the Systems Engineering and Marketing team to demonstrate the functionality of one of our newest reference designs from the building automation space, geared towards damper control and electronic expansion valves. The purpose of the board is truly to demonstrate motor control, using a variety of different control methods which are actively seen in the HVAC space today. We have also incorporated a variety of different features so that the reference design can be reflective of as many different use cases as possible. With that being said, let's get into the architecture of the board. So starting at the beginning of the board, you have two possible input options, 24 volts DC or 24 volts AC. Whichever option you choose can be selected with the onboard switch. Following the input power, the voltage will then pass through our TPS 16410 eFuse device, which regulates the onboard power and provides additional protection features. However, the main purpose of this design is to showcase our motor controllability. Here we demonstrate it by having two different motor drivers, the first being the DRV8428 stepper motor drive, and the second being the DRV8316C brushless DC motor drive. Either of these options can be selected to control the motor of your choice. The implementation of the control method is also up to the user. The board contains options for an input voltage signal from 0 to 10 volts, an input current signal from 4 to 20 milliamps, or a digital input, which is demonstrated using our ISO 1212. The purpose of the ISO 1212 is to essentially act as a binary valve where the high or low input signal corresponds to 0 or 180 degrees for the motor. Finally, the last feature we want to showcase on the board is the position sensing. This is done by using our 3D Hall effect sensor, the TMAG 5273. So there's a TMAG sensor located on the board. However, you can also use a remote TMAG sensor so that you can place the sensor directly next to one of the motors, where you can have a magnet on the motor so you can accurately sense the position. We will now be demonstrating the DRV8428 motor control utilizing a stepper motor. The board has been preloaded with the necessary code, which you can also find available on TI.com. Here you will see us turn on the power supply, which is going to the 0 to 10 volt input of the board. Each voltage point from 0 to 10 volts will represent a different angle position for the motor. You can see the motor moving to match the position as you alter the voltage. At 5 volts, you'll see it's approximately halfway between the 0 to 360 degree motor rotation. Now the other power supply in red is the input voltage to the ISO 1212. That power supply will dictate either a 0 degree or 180 degree position. You can see when we first turn it on, there is no movement as the motor is already set to 0 degrees. So to demonstrate it, we use the voltage control to reposition the motor to 180 degrees. And then we will turn the ISO input back on so you can see the motor revert to its original 0 degree position. The ISO input takes priority over any other input, so you can see that the voltage control does not take effect until that power supply to the binary valve is turned off. Then once again, you can see the motor modulating its position to match the input voltage. Here we will repeat the test using the brushless DC motor instead, along with the remote TMAG sensor to detect position. You can see as soon as power is supplied to the board, the motor begins to spin. However, until voltage control is introduced, it does not know the correct position. The motor stops spinning as the 0 volts corresponds to that 0 degree angle from the magnet. As we change the voltage to 5 volts, the magnet must be turned 180 degrees to cause the motor to stop spinning. As we modulate the voltage control, you can see the motor resume spinning below and above that 5 volt threshold only stopping when you meet that 5 volts exactly, as that's aligned with the magnet position. As we decrease the voltage below the 5 volt threshold, it spins in a clockwise direction, but when we increase it above 5 volts, it spins in a counterclockwise direction. Again, stopping only when it reaches that 5 volt position as set by the magnet. The red power supply once again represents the ISO 1212 control. It requires the magnet to be in a 0-degree position to stop the motor. You can see as we turn it off, the motor begins to spin as it needs to be reversed in the 180-degree position to match up with the 5 volt input. By referencing this design during your own design process, there are several benefits, including saving time and cost. It's a low-power system which utilizes some of our newest TI devices and targets upcoming trends in the HVAC space. For example, our magnetic position sensing technology is able to accurately detect motor position immediately without the need for calibration or an extended turn-on period of the motor. It also helps improve the overall efficiency of the system due to its ability to detect if a motor is stuck in an unwanted position. For example, if your room temperature is set to low, but the damper is malfunctioning and not moving to the correct position, the controller is typically unaware of the fault and will continue to inefficiently attempt to cool the room by pumping in more air. Additionally, the motor drives we showcase each have unique features of their own. The DRV8316C BLDC device contains built-in current sensing, which eliminates the need for external sense resistors. It is also able to internally monitor a variety of different faults, such as over or under voltage, over temperature, and over current, and communicate that back to the system's MCU over SPI. Our DRV8428 driver utilizes our newest SmartTune technology, which automatically adjusts to an optimal decay setting, which is able to quickly adapt to changes in the system, ultimately resulting in a quieter, smoother, and more efficient motor operation, eliminating the need for any additional tuning. Thank you so much for watching. Please visit TIDA010950 on TI.com to access the design guide and find more information.